What I'm going to do now is prove something called Pascal's law. It's the statement that the pressure at any point in a fluid is the same in all directions. So there's no directionality to the concept of pressure. So let me prove that to you using a little infinitesimal cheese wedge that I've drawn here. And what I'm going to do is I'm going to sketch different sides of it. Like one side is delta x, dimension delta x, another one delta y, and another one delta z. And I'll basically cut a plane that goes in half, long ways down one of the sides. And I'll call that hypotenuse distance delta s. I'll draw three pressures that act in the y, z, and then a combined y, z direction. With the one that's at an angle, I'll just call P for pressure. And what I want to show you is that the pressure that would have to act in the y direction to counteract the y direction force from the one at an angle, it turns out that those pressures are exactly the same regardless of whatever the angle is. So if you make a force balance in the y direction or along the y direction, then the sum of the forces, at least in static equilibrium, should be zero. So the pressure acting on the left face is P, or the force is P sub y times its area, which is delta z delta x. The force that counteracts that is the one along the hypotenuse, given by minus P times, since there's an angle theta, so that's sine theta times the area, which is delta x times delta s. But you can project the dimension delta s onto delta z. So delta z turns out to be equal to delta s times sine theta. And so what you'll see is that there's some cancellation that ensues. In the end, what you find out is that P sub y, or the pressure in the y direction, is exactly equal to P, the pressure at literally any angle. You can do the same force balance in the z direction, and so in that case, P sub z times its area, which is delta x times delta y, should be balanced by the downward forces, which include the hypotenuse, so minus P times delta x times delta s acting at an angle that involves the cosine of theta. And then there's another term that involves the gravitational force of the wedge, if we're including that. So that's the density times the volume times g. So that's rho g times delta x, delta y, delta z divided by half, since it's a triangle. And again, I can look at some of the dimensions. So like delta s can be written as delta y divided by cosine theta. And you'll see then that the two cosines actually cancel with one another. And then I can divide by delta x times delta y, which exists in all the terms, which gives you P sub z minus P minus a term that includes the weight. But if I look at the weight term, it actually has a delta z in it, which I know it's an infinitesimal element. So that term's actually incredibly small. So the only terms that are actually there are the p and the pz, and therefore those two things must be equal to one another. Although the little infinitesimal element doesn't allow you to say anything about the x direction, you can imagine doing the same derivation where I just turn the cheese wedge by 90 degrees, rotating it about the z-axis. If I were to redo it, anything that was happening in the y direction would now be happening in the x direction. And so by extension, the pressure in the x direction is also equal to the pressure along the hypotenuse, which again was at any arbitrary angle. So therefore, the pressure that acts at any angle in the x, y, and z direction is exactly equal to the pressure at any other angle that I'll just call P. So we won't really worry about the directionality of pressure. We'll just say that there is a thing called pressure, and it acts in every direction.